3 Atlas once again left the public stunned as it passed through perihelion, the closest and most dangerous point to the Sun for any comet. In the history of observations, objects that follow similar paths rarely keep their shape. They crack, release chaotic jets of gas, lose control, and in many cases break apart completely within a short time. But this time that did not happen. The latest images from the Hubble Space Telescope show 3 Atlas appearing sharp, stable, and almost intact. No fractures, no signs of chaos. This unusual calm has raised a question that scientists cannot ignore. Is this truly normal behavior for a comet? Or does 3 Atlas hide something far more complex beneath the surface? Perihelion is widely considered the most dangerous moment in a comet's life because it is the point where the object passes closest to the Sun and experiences the most extreme conditions in its entire journey. At this distance, solar radiation rises sharply in a very short time, pushing temperatures on the comet surface far beyond what its structure evolved to handle. For most comets, this sudden heat acts like a stress test that exposes every internal weakness at once. Frozen water and volatile gases begin to sublimate unevenly, turning directly from solid into gas as sunlight hits different areas of the surface at different angles. This process creates internal pressure that builds faster than the material can safely release it. As pressure increases, cracks form inside the nucleus, often invisible at first, but growing rapidly as gases force their way outward. These fractures then trigger jets that fire unpredictably, changing the comet's rotation and pulling material away from the core. Once rotation becomes unstable, the entire structure starts to wobble, and in many cases, large fragments break free. Historical observations show that this phase is when comets lose their clean shape, develop distorted comas, and leave behind chaotic debris clouds. Some comets partially survive perihelion but emerge stretched, split, or visibly damaged, while others completely disintegrate within days. Because of this, astronomers treat post-perihelion images as critical evidence of a comet's true physical limits. It is the moment when models expect to see disorder, asymmetry, and clear signs of structural failure. This is also why telescopes around the world closely monitor objects before and after perihelion, searching for clues that confirm or challenge those expectations. On November 30, 2025, the Hubble Space Telescope captured 3 Atlas roughly 1 month after it passed this exact danger point. By every standard assumption, this was when damage should be easiest to detect. If internal cracks had formed, they should now be visible in the shape of the core or the distribution of surrounding material. If jets had fired unevenly, the coma should appear distorted or pulled off axis. If mass loss had accelerated, the object should look less compact and less controlled. In other words, perihelion should have left fingerprints all over 3 Atlas. That is why this moment matters so much. The question is not whether 3 Atlas experienced extreme stress because it did. The real question is whether that stress left any trace at all. For a typical comet, the answer is almost always yes. So when the data suggested otherwise, it forced scientists to pause and look closer. If perihelion is designed by nature to reveal weakness, what does it mean when an object appears to pass the test without visible harm? And if this survival looks different from everything we expect, what exactly did Hubble see when it looked directly at the heart of 3 Atlas? What Hubble recorded after perihelion was not absence of detail but the presence of order where disorder was expected. The image taken on November 30, 2025 showed the core of 3 Atlas as sharp, compact, and clearly defined with no stretching or elongation along any axis. This matters because internal stress usually pulls a comet's nucleus out of shape once fractures begin to form. In damaged comets, the core often looks smeared, doubled, or uneven, reflecting internal breakup that cannot be hidden at this stage. In the case of 3 Atlas, none of those signs appeared. The nucleus remained tightly concentrated, suggesting that internal cohesion was still intact. Equally striking was what Hubble did not see. There were no visible cracks, no separated fragments, and no evidence of the nucleus splitting into multiple components. If fractures had opened during perihelion, even small ones, the Hubble Wide Field camera would likely have exposed them through irregular brightness patterns. Instead, brightness remained centered and controlled. Surrounding the core was a broad cloud of material that expanded smoothly outward. This coma appeared roughly circular and evenly distributed in all directions. There were no sharp plumes cutting across it and no directional streaks pulling material away from the center. In unstable comets, the coma often becomes lopsided as jets push gas and dust harder in one direction than another. Here, the expansion looked balanced, as if released under steady conditions rather than explosive ones. This symmetry is critical because it rules out the idea that Hubble simply missed the damage. The telescope did not capture a blurry or incomplete view. It captured a system that appeared organized at a time when chaos should dominate. Comparing this to known post-Perrin comets makes the contrast even clearer. Typical comets show warped comas, twisted tails, or uneven brightness caused by uncontrolled outgassing. 3 Atlas showed none of these features. Instead of looking exhausted or broken, it looked composed. This does not mean the object was inactive or unchanged after perihelion. It means the processes at work were not violent enough to tear the structure apart. That distinction is crucial because stability at the core does not rule out activity elsewhere. Hubble's tight focus revealed order at the center, but it could not show everything happening around it. To understand whether 3E Atlas was truly calm or quietly doing something else, scientists needed a wider view. And when that wider perspective came into focus, the story began to shift in an unexpected direction. The picture changed once scientists stopped looking only at the core and stepped back to observe 3 Atlas from a wider angle. From this broader perspective, the object no longer appeared simply calm or static. Instead, it showed clear signs of ongoing activity that could not be explained by leftover debris from perihelion. Observations from the ESA JUICE spacecraft were especially important because they captured 3I Atlas from a different position in space. JUICE was not using a dedicated science camera, but a navigation system designed to track movement and orientation. Even with that limitation, the data revealed structures that Hubble's tight focus could not see. 2 distinct tails appeared, each behaving in a very different way. The first was a plasma tail, thin and sharply defined, stretching directly away from the object. This tail followed the direction of the solar wind rather than the object's orbit. Plasma tails form only when ionized gas is actively stripped from an object and pushed by charged particles from the sun. They do not persist without a continuous supply of fresh material. Below it appeared a second structure that told a different story. This was a dust tail, broader and heavier, drifting at a different angle and moving more slowly. Dust particles respond to sunlight through radiation pressure, not electromagnetic forces. Because of that, dust tails curve and lag behind in ways plasma tails never do. The key point is that these 2 tails follow different physical rules. They separate only when new material is being released at the moment of observation. If the activity had ended near perihelion, the structures would blur together or fade unevenly. Instead, both tails were visible at the same time and clearly separated. This confirmed that 3I Atlas was not just surviving after perihelion. It was actively interacting with its environment. The presence of both plasma and dust tails showed that gas and solid particles were being emitted simultaneously. That behavior requires an internal process capable of sustaining release over time. It also means the object was not simply cooling down after stress. It was still doing work. This wider view also resolved an important misunderstanding. Stability at the core does not mean inactivity overall. The inner structure could remain intact while controlled release occurred at specific locations. That combination is rare for comets after perihelion. Most objects that release material this late do so in a chaotic and uneven way. Here the activity appeared organized rather than violent. 2 spacecraft observing from different angles were telling the same story. Hubble showed order at the center. JUICE revealed motion and separation beyond it. Together, they painted a picture of a system that was stable where it mattered most and active where it needed to be. This balance between control and release set the stage for the next discovery. When scientists returned to the Hubble images and examined them more closely, hidden structure began to emerge beneath the surface of apparent calm. At first glance, the original Hubble image of 3E Atlas appeared smooth, balanced, and almost deceptively simple. The light distribution looked even. The coma appeared round, and nothing seemed to break the sense of stability left after perihelion. For a casual observer, the image could suggest that nothing unusual was happening at all. However, astronomers know that raw images often hide important details, especially when an object behaves outside expected models. Subtle structures can be buried beneath overall brightness, invisible unless the data is carefully processed. To reveal these hidden features, scientists applied a series of enhancement techniques to the Hubble images. These methods are designed to amplify faint variations in brightness and expose patterns linked to motion and rotation. Once these filters were applied, the apparent symmetry of 3E Atlas began to fade. The inner coma no longer appeared perfectly circular. Small but consistent distortions became visible near the core. Brightness shifted slightly from one side to another, suggesting that material was not being released evenly. This alone hinted that the object was more active than the raw image suggested. As processing continued, the structure became clearer. Two distinct jets emerged from opposite sides of the nucleus. They were not chaotic or scattered. They were narrow, focused, and aligned in a stable configuration. One jet extended in the general direction of the Sun. The second extended in the opposite direction, forming a pronounced antitail. This feature immediately set 3I Atlas apart. Antitails are rare because they require very specific conditions to appear clearly. They depend on precise geometry, timing, and a controlled release of material. In most comets, rotation is too unstable after perihelion to maintain such a structure. Random tumbling smears the dust and destroys the alignment. In this case, the antitail remained clean and sharply defined. Its estimated length reached nearly 37,300 miles. That scale alone rules out a brief or accidental event. Maintaining such a structure requires steady rotation and sustained directional outgassing. The presence of two opposing jets also carries important meaning. Jets arranged in this way suggest fixed source regions on the surface rather than spontaneous eruptions. This implies that the internal structure of 3 Atlas remains organized. Material is being released through controlled pathways instead of tearing free under pressure. This finding aligns closely with what was seen from the wider perspective earlier. Jewett detected separate plasma and dust tails indicating active release. Hubble's processed images now showed where that release was originating. Together, these observations removed the illusion of complete calm. The object was not inactive. It was operating in a structured manner. What looked stable in raw images was actually a balance between control and motion. This balance is extremely unusual for an object that has just passed perihelion. Rather than collapsing or shedding material unpredictably, 3 Atlas appeared to manage its activity. This realization marked a turning point in how the data was interpreted. Once clear structure was visible, the behavior could no longer be dismissed as random. It became something that could be compared against models and predictions made before the observation. And when those earlier calculations were placed next to the newly revealed geometry, a deeper connection began to take shape. What made the newly revealed structure of 3I Atlas truly unsettling was not just its shape, but the fact that it had already been anticipated. Before the Hubble image from November 30, 2025 was ever released, scientists had begun modeling how this object might behave after perihelion. These models were not built on speculation, but on physics that assumes forces act in consistent and measurable ways. If an object follows chaotic behavior, its future position and shape become almost impossible to predict with precision. But if an object behaves in an organized manner, its motion leaves clues that can be calculated in advance. One of the key predictions focused on where released material would appear relative to the core. Instead of dispersing randomly, the model suggested that fragments or dense material would drift into a specific region closer to the Sun. This material would not trail behind in a typical dust tail. It would form a sunward structure shaped by rotation, radiation pressure, and non-gravitational forces. The prediction went further. It described the expected geometry of this feature: narrow, elongated, and concentrated rather than diffuse. It also estimated its scale. By late November, the structure was expected to stretch tens of thousands of kilometers from the nucleus. When the processed Hubble images were examined, the match was striking. The antitail extended to roughly 60,000 kilometers. Its direction aligned precisely with the predicted orientation. The overall shape followed the same teardrop L-like geometry described in earlier calculations. This was not a vague resemblance. It was a close correspondence in both position and form. That level of agreement matters because chaotic systems do not behave this way. Random outgassing produces messy, unstable features that shift unpredictably over time. Small changes in temperature or rotation usually lead to large changes in appearance. Yet here the predicted structure appeared almost exactly where and how it was expected. This forced a re-evaluation of how 3E Atlas was behaving internally. If the object were simply reacting to heat in an uncontrolled way, such precision would be impossible. Instead, the data suggested that release of material followed a stable pattern. Rotation appeared steady. Source regions seemed fixed. Forces acting on the ejected material behaved consistently over time. This does not mean that every detail was known in advance. It means the system followed rules rather than chance. In science, this distinction is critical. Predictive success strengthens confidence that the underlying assumptions are pointing in the right direction. When a model built before observation aligns with real data afterward, it signals that something fundamental has been captured correctly. In the case of 3I Atlas, that fundamental point was order. The object was not simply enduring stress. It was responding to it in a controlled and repeatable way. This realization shifted the focus of the investigation. If behavior followed predictable patterns, then randomness could no longer be blamed for the anomalies. Attention turned toward deeper questions about composition and energy. Because if the motion was organized, the material and power driving it had to be capable of supporting that organization. And when those properties were examined next, they introduced a new set of contradictions that standard comet models struggled to explain. When scientists began placing all available data next to each other, a series of contradictions became impossible to ignore. The first issue appeared in the chemical profile of 3I Atlas. Spectral measurements indicated an unusually low water content compared to typical comets. Most comets are dominated by water ice, often making up the majority of their mass. In contrast, 3I Atlas showed only a small fraction of water-related emissions. At the same time, metallic signatures stood out. The ratio of nickel to iron appeared far higher than what is normally observed in cometary material. Such concentrations do not easily fit objects formed in the cold outer regions of a planetary system. Energy behavior raised another problem. 3I Atlas produced detectable X-ray emissions, a feature that usually requires large volumes of gas interacting with solar particles. Yet visible mass loss remained limited. The amount of material leaving the object was not enough to explain the observed energy output. Non-gravitational acceleration added to the puzzle. The object changed speed in ways that gravity alone could not explain. In standard comet models, this effect comes from uneven gas release. Here, the acceleration appeared without the expected debris cloud. Orbital behavior completed the picture. 3 Atlas followed a path unusually close to the plane of the planets. It also experienced a sequence of close approaches to major worlds. For an interstellar visitor, this alignment is statistically rare. Each of these features could be explained on its own. Exotic chemistry might explain composition. Unusual outgassing could explain acceleration. Chance alignment could explain the orbit. But when combined, the traditional comet model no longer fit cleanly. What emerged was not a single anomaly but a pattern of tension between expectation and observation. This does not demand a radical conclusion. It demands careful reconsideration as new ultraviolet data and deeper analysis approach. 3 Atlas stands at the edge between known categories and something not yet fully defined. The latest images from the Hubble Space Telescope have changed the story of 3 Atlas once again. After passing perihelion, it did not fracture, collapse, or spin out of control. Instead, it remained stable, released material in an organized way, and revealed structures no one expected to see. From unusual tails to precise motion and strange chemistry, every new detail deepens the mystery. And this is not the end. More Hubble data and upcoming analysis are still on the way. As new images continue to arrive, we will keep tracking every update on 3I Atlas. Because whatever this object truly is, it clearly has not finished revealing its secrets yet.